Hey everyone, this is the third and final video for section 2.1 where we discuss limits and a little bit of rates of change. What we're going to do in this video is go back to something that we skipped in the first video. Going back to the strategies we have for finding limits, we discussed all of these strategies except for the fifth one, the sandwich or the squeeze theorem. So let's go there. This is a really long section. I promise they're not always this long. Okay, here we are. So, fun fact before we begin, the sandwich or squeeze theorem is one of Sal Khan's favorite math theorems, and it's just because of the fun name, or the fact that the name actually is pretty nice for what we're going to be doing with this theorem. Okay, I'm actually going to be using a little example that Sal Khan uses as an introduction to this theorem. Okay, so take a look at this picture here, and let's just focus on these three students right here. Okay, let's just say that, it's a really bad circle. Let me try that one more time. Let's just say that in math class, okay, it's always, always, always the case that this student scores the lowest out of these three on the math tests, okay? And it's always the case that this one up here scores the highest, okay? It's just like a fact that this one scores the lowest and this one scores the highest out of these three. That means that the friend in the middle here is just always somewhere, her score is somewhere in between this lower score and this higher score, okay? So we could sort of set that up as a little compound inequality here. This student's score is always less than or equal to this student's score, and that student's score is always less than or equal to this student's score, okay? Now, let's say that out of this test, they're taking a test right now, right? They get it back, and this student scored a 96, okay? The student who typically scores the highest, she also scored a 96, okay? So what does that say about the student in the middle? What does her score have to be? Well, if this compound inequality always holds true, then it must be the case that she's scoring a 96 as well. Does that make sense? If the lower score is a 96, the higher score is a 96, then that student in the middle must have also scored a 96. And so that's the basic principle behind the sandwich theorem. And now you're going to see it symbolically in a less fun format here. Well, maybe you think it's fun. I think it's fun. Let's call it fun. Okay. So what we have here is a compound inequality setup. And if you can set up a compound inequality between three functions, and you can say that the limit as x approaches a value of the lower function, notice the f of x is the lower function, has the same answer as the limit as x approaches some value of the upper function. Okay, so it's kind of key to note here that these limits are the same. Then the sandwich or squeeze theorem says that the limit as x approaches that value of the middle function must have that same limit. Okay, let's jump straight into an example, and then we'll go back and discuss this theorem again in more detail. Okay, so for example 1, we are finding the limit as x approaches 0 of x squared sine of 1 over x. And for this first example, I just give you the functions that it is, that the function we are finding the limit of is in between. And so let's take a look at this graph over here. The red graph is our function, x squared sine of 1 over x, and we're trying to find the limit as x approaches 0 of that function. But what I'm showing you with this graph is that this function is always above the function y equals negative x squared, but below the function y equals x squared. And so from that graph, we could set up a compound inequality that looks like this. Negative x squared is always less than or equal to x squared sine of 1 over x, and that is always less than or equal to x squared. And that's probably the most difficult part of this theorem, is setting up that compound inequality. From there, we are going to be able to apply our limit as x approaches 0, and we'll be able to finish this problem off very quickly. However, before we do that, I just want to back up a minute and talk about where these functions, negative x squared and positive x squared, are coming from, because I remember thinking that to myself. I remember thinking, how am I going to know what functions to use for my compound inequality? Okay, well, for beginners, sine and cosine are really good functions to start with when learning the sandwich theorem, because sine and cosine have known range values that are real numbers. So think about like the graph of, just let's start with something very simple, the graph of y equals sine x. You know what? Just in case you can't visualize it, I'll put it here. Y equals sine of x. Okay, I'll do a zoom 7 trig viewing window. And I'm talking about the range again, like what are the values that come out of sine of x? They are always somewhere between -1 and +1, right? And cosine is the same, it's just shifted. So that's a starting point that you can use if you're going to try to do a sandwich theorem. Okay, now I know that here I don't have sine of x, I have sine of 1 over x, but that doesn't matter. That's not going to change the range. It's not going to change what comes out, the bounds of what comes out. So if you take a look at this sine of 1 over x function, it is also still between -1 and 1. Okay, we can see that in the table here. So again, what we're going to do to start is we are going to say that sine of 1 over x has a range of -1 to 1. Now we do need a little bit more, right? We have the function x squared sine of 1 over x. So what we really want here in the middle is x squared sine of 1 over x, and that means we need to multiply each part of this compound inequality by x squared. Now, good news about multiplying by x squared, that is always a positive value, so that does not change the direction of the inequality symbols. Meaning you can say from there that -x squared is less than or equal to x squared sine of 1 over x is less than or equal to x squared. And that was the compound inequality that I wrote from this graph. So you don't necessarily have to think about functions that your function is sandwiched in between. You could pick apart your function, and if you know part of the function's range, then you could start there and try to add on to get where you need to be. Okay, now let's go back to the theorem, the sandwich theorem, and let's think about what we should do next. So we just established this compound inequality. We have a lower function, an upper function, and our function in between. Now what we are going to do is we're going to apply the limit to the lower function and the limit to the upper function, and we're going to hope that they have the same answer, the same value. Okay, I remember students always asking me, well, what if they don't? I usually tell them, well, then sandwich theorem probably wasn't the right way to go. Move on, try another method. Maybe it doesn't exist, who knows? You'd have to do more analysis. Here, it's going to work out for us, of course it is. Okay, we're going to do the limit as x approaches 0 of -x squared. And skip the middle for now. We're going to do the limit as x approaches 0 of x squared. Now those do end up both being 0, right? You can just use substitution here. -1 times 0 squared is 0. 0 squared is 0. And since they do match in this case, okay, it is really important that you get the same answer for both of those limits, which we have here. We can say, therefore, the limit as x approaches 0 of x squared sine of 1 over x is also equal to 0 by the sandwich theorem. Yay. And so what you are going to see for the most part when we practice these problems in class is that you are going to have some sort of function that involves sine or cosine. because that's a nice easy starting point. And really, I just want you to get used to the process right now of setting these up and recognizing that this is a theorem you can use at times. Okay, finally, we are going to discuss a limit that I told you this in the first video, is really important to know. However, we never proved it. I just sort of showed you that this is probably the answer, and then I told you it is the answer, and I told you to know it. And that is the limit as x approaches 0 of sine of x over x is equal to 1. Okay, so just so you know, a lot of the first parts to this proof have already been done, and I'm not going to talk about all of them in detail right now just because I want to keep this video pretty short. If you would like more information about where this comes from, you can ask me and I'll happily discuss it with you. It has to do with these areas. You're able to put them in a compound inequality. Okay, and it's really not that difficult to understand. Again, I just don't want to take too much time going over all of this to keep the video short. So from this information, from these areas, we are able to establish this compound inequality. I'm going to start way down here. Okay, now notice the variable has been changed from x to theta, and it explains here that, just to avoid the confusion of having an x-axis, they switched the variable that we're looking at here to theta. And so what I'm trying to do right now is, I'm going to get a different color. I am trying to prove that the limit as theta approaches 0 of sine theta over theta is equal to 1. Okay, I'm not going to write that yet, but that's what I want to sort of show here. I want this to be equal to 1. Okay, and I'm going to use this compound inequality as my starting point. If I know that sine theta over theta is in between cosine theta and 1, then I can take this limit as theta approaches 0 and apply it to those parts. So I'm going to write the limit as theta approaches 0 of cosine theta, and I'm going to write the limit as theta approaches 0 of 1. So I used the lower function and the upper function here. For this one, I can use substitution. Cosine of 0 is 1. For this one, I don't need to use anything. The limit as theta approaches any value of 1 is 1. If there's a constant here, that's your answer. They match, which is, again, something that you must have for the sandwich theorem to work. We have that here, and so therefore, we can go over here and say that the limit as theta approaches 0 of sine theta over theta is also equal to 1 by the sandwich theorem, or squeeze theorem, as Sal Khan likes to call it. Okay, I hope this was a helpful little intro to the sandwich theorem, and good luck with your studies. Bye!